Hi everybody, today we're going to go over a quick demonstration of how to use Simulink. We're going to start out with just a pretty easy first order differential equation. It's just linear with constant coefficients. So initially to pull up Simulink, you're just going to type Simulink into the command window with MATLAB running. This is going to quick open Simulink. You can also find it in the file tab on MATLAB. So the main idea is to translate an equation into basically a sequence of blocks, and then we're going to hook them together in the appropriate way to form a system. So the variables in the equations are going to become signals that vary with time. So these blocks, as you can see on the screen, they perform these mathematical operations on the input signals to generate an output signal. So as you can see commented here is just the differential equation that we're going to use. And the blocks are kind of just a general outline, but we're going to have to edit them to get the proper signals generated. So you can find these blocks basically in the browser library. So I'm going to open that really quick. As you can see, everything is kind of separated into these different categories. Commonly used blocks, obviously that's pretty helpful because it's going to be all the things you use most often. You can see here, there's the scope, which we have already on the screen. And then another important thing is the search bar. So if you know what you're looking for, like scope, it's pretty easy to find what you want to get a block on the screen if you know what you want to search. So once you get everything that you want on the screen, you're just going to connect it using these lines here. As you can see, the output is normally on the right side and the input's on the left. And you can just drag these lines across the screen to connect different blocks. You can also delete them if you make a mistake. It's pretty easy. Just press backspace. And then you can reconnect them in however way you want. Now, you can also split the line like this, as I'm doing on the screen. If you press Control, it's also Command on a Mac, and you can input it into the scope as shown here. Now, to kind of get this set up to model the equation that we're going to be using, we're going to have to change this block. So this is a gain block. You can just enter whatever you need. And for this equation, it's going to be 3. And then there's also another gain block here, and this one's going to need to be 2. Now, just because these lines are crossing doesn't mean the signals are technically crossing, but just to make it more clear, you can also right-click and go to rotate and flip, and you can flip the block so it's more clear what's the input and what's the output on this block. You can also, on these different subtraction or adding blocks, you can change the signs that are here. For this equation, we're going to need plus and minus, so you can just go ahead and change it. You can also see we have the integrator block. The 1/s is just because of the Laplace transform. And you can see we have a constant block here as well. We're just arbitrarily using the sinusoidal input. As you can see, if you open it, you can adjust different things like the amplitude, the frequency, etc. We're just going to go with the standard, the default ones for this. But you can go ahead and run the simulation by pressing this green arrow right here. And if you have your laptop with sound on, you can hear a beep when it's over. This is a pretty quick simulation, so as you can see, it just went by really fast. You can adjust the time here as well, and then you could double click on scope, and you're going to get the output. So the scope just gives you the x and y as a function of time. So you're going to see the y on the y signal on the top and the x on the bottom. Now we're going to pass it over to Kyle, and he's going to go over how you can compare different graphing functions.
So here we can see that we have the same first order differential equation that Amanda presented. We can see that we copied and pasted down the same first order differential equation, but in the bottom one here, I made a few edits to the sine wave. Now we can go ahead and run the simulation and click on each scope individually, and we can see that it gives us a good graph of the change to the input signals again. However, we have to click between the two in order to see them side by side, and this can get a little tedious. So one of the things that Simulink can do is that it can log these signals. So if we highlight the signals that we want, we can see this little blue Wi-Fi signal come up next to them. This is indicating that it's logging those signals now. If we do that to both, we can go ahead and click the run and open up our data inspector and select the graphs that we want to see. So for that small change in the amplitude and the frequency of the sine wave, we can see exactly how the graph changes on the same x-axis. So this can be really useful if you're going back and forth between one or two equations and want to see what small adjustments are going to do to your final graph. So now we'll go ahead and throw it over to Haley to talk a little bit more about how to use the subsystem function.
All right, so next we're going to show you how you can use subsystems to simplify what your overall system looks like. For complicated models, this becomes really important, but we are just going to show this using some basic models. The first subsystem we have is already on the screen, and Amanda actually showed it earlier, so you can see it's the same parameters and blocks as before. So then we can go back to the main screen by clicking up here, back to the file name, and you can see subsystem 2 is also there. This one you can double click to view as well. And this is a new one, but again, just simple, same blocks that we talked about previously. So from the main screen then, you can see that I had to label this, but the input into subsystem 1 is X, the output is Y, and then in subsystem 2, X and Y are the inputs and Z is the output. So we can actually go ahead and connect these subsystems. In this case, we're going to connect where the Y's are. So that would look like this. You just drag the arrows. And to actually see anything with this kind of system, we are going to need to add in some more blocks. So we'll go to the browser again. And first, we're going to need a source. So we're going to grab a pulse generator. Okay, that's loading, it looks like. Okay, and then we're also going to get some commonly used blocks like scope we're going to need, and then also a new block is the mux. So the mux is going to be useful for combining multiple different inputs that we want to display on the final graph for the scope. So we have to double click and change the number of inputs. We're going to have 3 in this case because we are going to show X, Y, and Z. And then we just go ahead and connect everything. This will be the source here. And then X also is connected here. And then Z, our main output, we bring to the mux. And then we also have a line for Y, which we can connect here. And we'll just drag this down really quick. Okay, and then lastly, we want to show X, so we'll connect that right here. And then we can run that and see it on the scope here. Okay, so now that we've looked at some of the basics of Simulink, we're going to look at how we can apply it to a common industrial controller, the PID controller. So to find your PID block, just go to your library, hit continuous, and then your PID controller is right there. I've already set up a little demo where we just have a unit step function, a basic transfer function, and a scope. This is a closed loop. So if you look at your PID controller, you can see there's a couple of things you can change. One of them is the form. There's ideal and parallel. These are almost the same thing. As you'll notice as I switch between the two, the only difference is in parallel, P is kind of multiplied through into I and D, versus if you go to ideal, P is factored out. So if you want to switch between the two, just multiply or divide based on what your goal is or what you're starting with. So as you can see here, you change P, here you change I, here you change D. If you have a tau I value, your I is just going to be 1 over that. And then the other thing to note is the filter coefficient. Simulink does not allow you to use an unfiltered derivative. It's because this avoids derivative kick, which means if you have a really fast change, you would have a ridiculous response and it would cause instability. So to avoid that, Simulink just forces a derivative filter. And that's kind of the basics of a PID controller. And if you apply it to a more complex system, here we have a disturbance coming in, and then here's your control system with your PID. This is a second order transfer function.
So we're just going to look at how like changing a few things might impact your response. If you look at this one, we're going to have a P of 10. And for this top response, the P is 4. And so if we run this, take a look at our output, you can see that with a higher P, you get a faster response, which makes sense. However, you do have to be a little bit careful because as you increase P too much, you might get instability. Another thing to note is that your derivative filter can have a really big impact. So again, if you change this, make it really small, leaving everything else the same. Now, all of a sudden, you have oscillations in your response. So if you're getting oscillations, things you can look to do are decrease P or increase your derivative filter. And that about wraps it up.